Hey guys, welcome back to lecture 6 on multiple linear regression. But before understanding it, remember what we learned in simple linear regression. We have an independent variable x, one dependent variable y. For example, our study gets you to the exam score. The formula is y is equal to mx plus b, where y is the predicted output, x is the input, b is equal to intercept, and m is equal to coefficient or slope. The model assumes that there is a linear relationship between x and y. Now, what is a multiple linear regression? Suppose we want to predict a house price. Instead of using only area, we have x1, that is area, x2 equal to number of bedroom, x3 equal to number of bathroom, x4 equals to age of the house. So now we have multiple independent variables. That's a multiple linear regression. More than two variables when we are dealing with, it's called as multiple linear regression. So the formula here goes as y equals to b0 plus b1 x1 plus b2 x2 plus b3 x3 till bn xn. So what does the formula mean? Suppose each feature has its own coefficient. For example, b1 tells us how area affects predicted price. B2 tells us how bedrooms affects predicted price, and B3 tells us how age affects the predicted price. The important idea is we look at the effect of one variable while keeping the other variables constant. That's one of the most important thing to remember about multiple linear regression. What does linear mean here? Even though we have multiple variables, the relationship is still linear with respect to the coefficients. So with one feature, we can visualize a line. With two features, we visualize a plane. And with more features, mathematically it extends into a higher dimension. The assumptions of multiple linear regression is also important for us to know. First is linear relationship. We assume that the relationship between the independent variables and the dependent variables can be represented appropriately using a linear model. That means they have a linear relationship with each other. Independent observations, we assume that the observations in our data set are independent of each other. For example, one customer's observation shouldn't improperly depend on another customer's observation. No serious multicollinearity. Our independent variables shouldn't be too strongly related to each other. For example, house area in square feet and house area in square meters. These are basically measuring the same thing, and this can create problems for the model. Another example I can give is when we are predicting salary, age and experience are highly related with one another. With increase in age, there is an increase in experience. So we tend to avoid one of the two variables as it can create problem to the model. Constant variance, we assume that the variability of relationship is reasonably consistent across the range of predictions. That was about multiple linear regression. I hope you understand that part before moving. Now, we will see another linear regression, which is polynomial regression. Now, imagine our data doesn't follow a straight line. For example, experience and salary. Maybe salary increases slowly at first and then increases faster. A straight line might not represent that relationship well. So instead of using y is equal to b0 plus b1 x1, we add powers of x. So the formula that you should remember for degree 2 polynomial regression is y is equal to b0 plus b1 x1 plus b2 x square. This is called quadratic regression. And degree 3 y is equal to b0 plus b1 x1 plus b2 x square plus b3 x cube. This is cubic regression. In general, the degree tells us the highest power of the x used. So why is it called polynomial regression? Now, when you have studied maths, you have seen the equation like 2 plus 3x plus 5 square. So that's generally a polynomial. The important thing to understand is polynomial regression allows us to model a curved relationship instead of restricting ourselves to a straight line. So in the last video and in multiple linear regression, we were talking about a straight line relationship between input and output. But necessarily in real life, there can't be variables which will have a straight line relationship with the output. So for that, we use polynomial regression. Is polynomial regression still linear regression? Yes. Even though the relationship between x and y can be curved, the model is still linear with respect to its coefficients. For example, y is equal to b0 plus b1 x1 plus b2 x square. So the coefficients b0, b1 and b2 are still linear in this equation. So polynomial regression can be treated as a type of linear regression after creating polynomial features. Multiple linear versus polynomial regression. This is probably the most important comparison. For multiple linear regression, we ask the question that how many input variables do I have? Example, and for that we use the formula y is equal to b0 plus b1 x1 plus b2 x2 plus b3 x3. When we have multiple features, we use this formula. But for polynomial regression, we ask question as, is the relationship between my features and target curved? And there we use formula y is equal to b0 plus b1 x1 plus b2 x square. So we are adding powers to it. So if you remember only two things from this video, remember this. Multiple linear regression means using multiple input variables to predict one output using a linear regression model. Polynomial regression means adding powers of our feature so that the model can capture a curved relationship. Multiple tells us about the number of features. Polynomial tells us about the form of the relationship. And that's the basic theory behind the two important regression techniques. I hope you understand the concept. Please subscribe to my channel and make sure you like and comment.